Good afternoon. I'm David Chappell. Welcome to this talk on NoSQL on Microsoft Azure, an introduction. I'm so happy to be here. Don't you love shows like this? It's a pleasure to be at Ignite. Are you happy to be here?
Yes.
Yes, good. Thank you. Thank you. Before we start, a couple of comments. First, an introduction. There's no code in this talk. There are no demos in this talk. And the reason is that I believe with all of my heart that there are three aspects to new technologies to understand: what they are, why you should care, and how to use them. I believe also that intro talks like this should almost always be about what and why. This talk is all about what and why for NoSQL on Azure. It is not about how even a little bit. There's no code, there's no demos. If that's what you want, sorry, you might want to exit, because we're going to do concepts. Lots of diagrams, lots of pictures. Okay? Also, it's worth pointing out that we're going to focus on NoSQL on Azure, but a big part of the story for the data platform in Microsoft's world remains SQL. And so after this session, in a room right nearby, there's another talk on the evolution of SQL Server, which is all about the next release of SQL Server, which I encourage you to attend if you're interested in that. Okay? So with that, let's start. Here is the fundamental contention I would make, the thing that drives, that animates this presentation. It is this. It is that NoSQL technologies are a fundamental part of Azure today. If you have not been paying attention for the last, 6 to 9 months, you probably missed this, because a number of things have changed, new things have appeared on the Azure platform that support a range of NoSQL technologies. And so that is the assertion which I will try to prove to you, in some sense, for the next 75 minutes. So let's think about data. Data, surely, is as critical as ever. In fact, I wonder if you agree. I would assert that data is what the people who pay us care the most about. I have done many talks around the world to thousands of people on cloud computing. And in every one, people always ask me, David, they say, what about the security and safety of our data in the cloud? Nobody ever asks about the security and safety of their code. It's about the data. People really care about their data, all right, fundamentally. That's the main thing. And I kind of wish things were as they once were in the past. Some of you perhaps remember this. Our field is now called information technology, which sounds very cool. But for a long time, it was actually called data processing. IT is much cooler, isn't it, than data processing? We could have higher salaries in IT than data processing. But I almost wish we were still called data processing, because that puts up front the thing that matters so much to people who pay us, which is data. Data is central to what we do. It is central. And it's also much more plentiful. Storage costs have dropped so much, as you know. There are many more sources of big data, web-scale apps, IoT, and lots more. As a result of this, new data technologies abound. I mean, come on, you know this, right? Database technologies were really boring for a long time. For decades, there was SQL and relational databases, and then there was more SQL and more relational databases, and it was boring. It is not boring anymore. It's now a really exciting area in our field. So we've seen the growth of NoSQL, of big data analytics, of search, of all kinds of things. I know people who believe that SQL is over, who think that relational databases are an artifact of the past. The future belongs solely to NoSQL, non-SQL approaches. Those people are nuts. Those people are just wrong, because SQL is forever, it appears. At least it's got decades to run. I got a royalty check last week from Wiley, a publisher I've worked with, for a book I wrote in 1989. There has been, I admit, an update about 10 years ago, which changed almost nothing except the copyright date on the book. The book is a visual introduction to SQL. It's one of the early SQL books. I wrote it in '89. That book is still being used this semester in a course at MIT. That is reflective not of the book's quality, but rather of the enormous lock-in that data creates. We've got this massive, decades worth amount of data in the relational format. And so it's impossible to believe that we're going to have a world without SQL anytime soon. In fact, I'm going to argue in a few minutes that there are still lots and lots of cases, maybe a majority of cases, where SQL-based data is still the right approach. So in no way are we heading into the NoSQL era, I would argue. I would say, however, that while this is not the post-SQL era, it is the SQL Plus era, where SQL relational systems are no longer enough. We now have to do lots more things. In fact, I think about it like this. On one dimension, we are moving from a world that was SQL and only SQL to this SQL Plus world, where there's SQL and lots more. On a second dimension, we're going from an on-prem world to a world that's more and more cloud. And so what is the path for data going forward? Toward the upper right. The trend is toward a SQL Plus technologies in a cloud-oriented world. Thus, we are here today to talk about exactly those things. Okay? With me so far? Great. You know, I got to tell you, don't you love this room? In conferences, you usually have these giant rooms with walls of desks for the speaker. This is like, you know, a university. I'm back in graduate school. I like this a lot. All right. Data on Azure, NoSQL services. I don't know about you, but I can never think about something without a frame to put it in. I never care about details until I have a big picture in which I can position those details. So this is the big picture frame that I want to use for at least much of this talk. At the end, you're going to see I'm going to change this a bit to a somewhat different frame because the world is getting bigger all the time. But I find this frame useful to think about big sections of this space. So I would suggest you can think of data in two big broad categories. It's kind of a simple-minded approach, but bear with me. One of those categories is operational data, transactional data typically. It's the stuff our applications use to record, I don't know, sales of books from our bookstore, or vacation days, or any other application you want to work with. Operational data. Then we store that, we save it, we do analysis on it, it becomes analytical data. Operational data is generally read-write. Analytical data is generally read-only. Okay? Two big giant categories form the columns of my chart. The rows are going to be, unsurprisingly, relational, SQL, and NoSQL. So we have a simple four-quadrant structure to think about data in this world. So let's start in the lower left. The most familiar to many of us, relational technologies for operational data. In a Microsoft context, what does that mean? Well, it means SQL database, SQL server, might mean Oracle, MySQL, relational databases. And you're wondering, David, what do those colors mean? Why are there different colors on the text? I will tell you. The colors mean something. The stuff in yellow identifies managed services provided by Azure. So SQL database is a managed service, a relational service based on SQL Server that runs on Azure. It was called SQL Azure for quite a while, but it's now called SQL Database. The stuff in white represents traditional software, like SQL Server, Oracle, MySQL, that can run in Azure virtual machines, if you choose to. All right? So great. There's that lower quadrant. Here in the lower right, relational analytics. Again, SQL Server, Oracle, MySQL, you can run all those guys in Azure IaaS VMs to do analysis in the cloud. And last week, a couple of days ago, Microsoft announced some new things that would fit in this space, at least partially, like SQL Data Warehouse, which we're not going to talk about because they were announced like 3 days ago. The top row, our main focus for today, NoSQL technologies. In the operational quadrant, there are various categories that are commonly used for NoSQL. One of them is document store. Brief digression. I'm going to use the word store and database interchangeably here. There are people who think that's a mortal sin, because to them, database means something powerful and complex like SQL Server or Oracle. Well, these NoSQL technologies, you'll see, are often so doggone simple that they barely qualify in the minds of these people as databases. They call them stores instead. I have no strong views here, so I'll use the words interchangeably, but recognize that not everyone does. Document store is a big category here. We'll look at it in a few minutes. On Azure, there is a service called DocumentDB that provides a managed document store that you can use. There are also other document stores that exist as ordinary software that you can run in Azure VMs. The most well-known in this category is MongoDB. Another big category here, key value stores. If you don't know what these things are, I'm going to tell you. Don't worry. That's what you're here for, right? I'm starting with this categorization. Tables is the key value store service that Azure provides. There are lots of other key value store databases like React, and there's more. Column family stores. Again, HBase, one of the most well-known, available as a service on Azure. We'll look at it. There are others as well, like Cassandra, which you can run if you choose to in Azure virtual machines. We're going to focus this afternoon. We're going to focus on the things in yellow. We're going to talk about the built-in Azure services, primarily those in the top row that offer NoSQL. Okay? If you're a NoSQL fan, if you've read much at all about this space, you very likely know that there is a fourth category that is commonly talked about here. That category is called graph databases. And the most well-known example is something called Neo4j. You can run Neo4j in Azure VMs. You can use it on Azure. But there is, at the moment at least, no Azure managed service for a graph database. And so that's the primary reason why I won't be discussing it here today. Our focus is Azure managed services, and there isn't one for graph databases. Although you can run Neo4j in IaaS VMs if you want to. Why is there no Azure managed service for this? I don't know. One could hypothesize that it is because it's the least popular of these categories. But I don't know. Oh, by the way, I hope this is clear from the start. I don't work for Microsoft. So what I say here today is my perspective when opinions appear, okay? So I can't speak for why they didn't do this, but there isn't one, at least at this point. Thus, we're not going to talk about graph databases here. Finally, the last quadrant, upper right, NoSQL technologies, analytical data. Something really remarkable has happened there. Something that very rarely happens in our industry. It is that everybody, all the vendors, everybody else, has embraced one technology family for that quadrant. And that technology family is called Hadoop. On Azure, there's a service called HD Insight, which provides a managed set of Hadoop services. And this gets kind of messy, because originally, Hadoop was all about big data analytics. Today, as we'll see later, the Hadoop family spans more than just that. So it gets kind of confusing here, but I'll come back to that later on. What I want to do here is give you a big picture illustration of this whole space and what we're going to focus on, which is the things in yellow in that table. Okay. This is totally irrelevant, but I got to tell you this story anyway. When I wrote this book on SQL back in '89, it was the very beginning of desktop publishing, when guys like me could do their own book design and produce camera-ready copy. And so the publisher let me do this. And I was like, oh, this is so great. I could be a book designer. And by the time I was done with the book, I was actually more excited about the book design than about the content. You know, I got to work on the kerning and choose the fonts and do all that cool stuff. It was just great. Book comes out, and I'm deeply happy with the book design. I was so proud of it. I'm a book designer, not just a writer. So a little while later, 6 months, 9 months later, I'm talking to somebody from Wiley, the publisher, and they say, David, they say, you know, we use your SQL book as an example for newly hired book designers at Wiley. And I'm like, oh, wow, that's so great. And then he finished his sentence. He said, this is an example of what not to do in book design. And I was struck by the fact that having the tools, I could buy the software, and having the talent are very different things. Right? So I had the tools, but I lacked the talent completely. By the way, I see people taking pictures of my slides, which is fine, no problem. But just be aware that they're available on the TechEd site. You can also send me mail, send you a PDF of the deck. So you don't have to do that. You can if you want to, of course. All right. Let me start with a really quick look at SQL database. And the reason is I'm going to compare the NoSQL technologies against this. I'm going to use the same general example. So SQL database, as I said earlier, is a managed relational system based on SQL Server. It's very much like a managed SQL Server in the cloud. As I'm sure you all know, relational systems have tables. The tables have columns. Like, for example, suppose this database is supporting an online game of some kind where I want to keep track of my users. They have IDs, they have names, the country they're from, how old they were, when they last used it. So I have a column for all of those things. Columns have types. This thing called schema defines your columns, column types, and so on. So int char, int date, whatever. Okay, great. There are then rows in the table. Each row has a primary key, some unique value, and other information. There's something for every intersection in the table, every cell. Notice that the rows are not sorted. In the relational databases, by definition, the rows are not sorted by primary key, which is interesting. I'll come back to why that's interesting later on. Applications submit, of course, SQL queries, and they get back relations, rows and columns. You all know this. Fine. I'm going to show the same example in several NoSQL technologies to show how it might map into those other worlds. Before I do, though, let me discuss something else. A few times in this session, I'm going to digress into a technology basics slide because there are a number of very similar, interesting things that apply across NoSQL in general. And so when those things come up, I'll do a technology basics slide. The first one is sharding. It's sharding, okay? And here's the idea. Suppose I've got a database, an ordinary SQL Server, MySQL, whatever, okay? Traditionally, what I do is I put all the data in that database on one machine, physical or virtual, on one machine. If I want to make that bigger, I want to scale more, what do? Answer, I buy a bigger machine, okay? Right, that's how I scale. I scale up, buying a bigger machine. There is a point, however, beyond which I cannot buy bigger machines. Even more, bigger machines get more and more and more expensive, right? And so I'd like a way to scale without scaling up on big, expensive machines, but rather to scale out by having lots of less expensive machines that I can spread my data across. Well, the way we do that, typically, is something called sharding. And the idea is this. And I've got a few machines, and I parcel my data. I break my data across those machines, physical or virtual. But I must somehow organize my data into shards in some rational, reasonable way. I should tell you guys, if you aren't afraid, you could come sit in the front row if you want. There's some seats down here. But here, for example, I've chosen a very simple thing. I just organized data by alphabet. The A's are in one shard, the B's in another, C's in a third. The point is, somehow you've got to break your data down into groups that make some sense so you can find things, which shard they're in. If I do this, I can now spread data across lots of cheap machines. I can scale much better, and the hardware supporting me commonly can cost less money. Great, sharding. Now, relational systems traditionally have not done sharding. You scale up instead because, in part at least, when you do this, you lose stuff. We are engineers in some sense, yes? Engineering is the art of making trade-offs. And so there are trade-offs here. One of the big trade-offs is this. When you shard data, typically, you can get atomic transactions that span only a single shard. You can only do transactions on data in the same shard. And the reason, at least one of the big reasons, is that if I try to do transactions, atomic transactions, ACID transactions, across multiple shards, I must do two-phase commit, which is slow and kind of painful. So generally, when you do sharding, you lose the ability to do transactions across multiple shards. The shard becomes the transaction boundary, and we'll see that over and over in NoSQL systems. Maybe you're wondering, well, David, you told us that relational systems commonly don't do this. Yet you've just described a relational system, SQL database, and then segued to sharding. Why? Well, it's an important setup for what comes next, but also today there is a feature in preview in SQL database called Elastic Scale that brings sharding to SQL database. Interestingly, though, as you might expect, if you use this feature in SQL database, what do you lose? You lose the ability to do atomic transactions that cross shards. No surprise. So, all right. I'm going to build this table throughout much of the rest of the talk to try to compare some of the more essential aspects of the technologies I'm talking about. Let's start with a SQL database. It is, of course, a relational system. The core storage abstractions that we see as users are tables, rows, and columns. The max database size in SQL database today is 500 gigabytes. That is assuming, as my slide says, that you're not using Elastic Scale, the sharding option. If you shard, you can get really big, right? Much, much bigger. But if you don't shard, then you're left with 500 gig as the size, max size. Query language, SQL, unsurprisingly. Transaction support, all rows and tables in your whole database. And again, that assumes that we're not using sharding, the sharding option. If you use sharding, you can only have transactions across the same shard. Secondary indexes, just so we're all on the same page. Here's the idea. In a relational table, as I showed you earlier, there's that primary key. The system creates an index on the primary key, like a phone book, to let you, man, that's a dumb analogy. Phone books are totally gone, aren't they? Whoa, what are we going to use for analogies for indexes here without phone books? Like a search index, actually. Anyway, indexes help you search for things much faster. And so it automatically creates an index in the primary key. You can also, in relational systems, typically, like SQL database, say, I'd like an index on this column as well. It'll build one for you. Those are called secondary indexes. And that is supported in SQL database. It lets you do things faster. It lets you find things faster. Store procedures and triggers, yes, written in a language called T-SQL. And finally, and this is interesting, pricing. The SQL database changed relatively recently how it prices. And if you're not paying attention, this is important. Because think about this. It's a service. It's a shared service running on a bunch of machines in Azure data centers. It's used simultaneously by potentially lots of users. Well, for most of its existence, SQL database did pricing based on size, how much data you stored, which kind of makes sense, you'd think. Except when you issued a query or ran a stored procedure, the performance you got was a function of how busy that shared machine happened to be at that moment. And because you've got these shared machines being used by people around the world potentially, it varied incredibly. A query performance could vary by a factor of 10, depending on what else was happening at that time on that machine. And so there were lots of apps that just couldn't accept a variation of a factor of 10. So Microsoft changed this last year. You now purchase guaranteed throughput. Pricing is based on throughput because that's what you really care about. So that's important. Before that change was made, there were plenty of people who did not believe SQL database was really a very useful technology because your perf could vary so dramatically. But now you buy perf, you buy throughput. That's how you're charged. It's a big improvement, I would argue. All right, great. Next. Why isn't SQL database enough? Why wouldn't we always just use SQL? Why do people use NoSQL on Azure? I would argue that there are variations here. There are typically three big reasons, three big things that drive people like you away from relations and toward NoSQL. One of them is scalability. To scale for lots of users and lots of data. Because commonly, NoSQL technologies can offer more scalability than pure relational systems. How do they do this? Well, as a pro, they do this by sharding. And so that's a con. When you do this, you lose some benefits of relational systems, like database-wide transactions. Because as we're going to see, these NoSQL systems all do scale by sharding. And so when you do that, you lose this broad support for ACID transactions. Trade-offs, engineering. A second big reason why people use NoSQL: to work better with different data formats. And today, that most often means JSON. Because if you're writing an app in JavaScript, let's say, you can serialize your app's objects and just store them as JSON natively if you're working with a NoSQL system that supports JSON, which, as we'll see, some do. And so you get to avoid the horrible pain of OR mapping, right? Great. These are subjective perspectives, but my perspective here is this. It is that originally, a primary driver, to me, the primary driver for NoSQL was scale. It was this. But now, with the rise of JSON databases, we'll discuss in just a minute here, I find that at least half the people choosing a NoSQL system for JSON are doing it because of this, because they want the data model. It's interesting. What's the con of that? Well, classic BI tools expect relations. That's changing with the rise of Hadoop and so on. But another big con, potentially, is that if I serialize, if I read out my objects as persistent data, great. They're wonderful to read back in from my app. They're great. But how does anybody else access that data? You might remember this, some of you. In the 90s, in the 2000s, there was a big push for a while toward object databases, which serialized C++ or whatever into persistent form. But they crashed and burned for various reasons, one of which was you couldn't share the data because nobody else could read it back in. It was in your object graph format. The same issue occurs here. Now, there are plenty of people who believe that sharing data from the database is itself an evil sin that you should never do. That's redundant, evil sin. Right? Are there good sins? I don't know. But it's a bad thing to do. They say you ought to share via exposed web services or something. Okay? So there's a debate there. But it's worth recognizing that unlike relational systems, which are very much designed to share data across multiple apps, that's what normal forms are about to a great extent. If you do this, very likely your data is going to be great for your app, but hard to share at the database level. And finally, the third big reason that I see people use NoSQL is this: to work with data in a more flexible way, which is in fact a polite way of saying no schema. Get rid of that evil schema. Great. No schema means flexibility and ease of use and a lot of pain down the line, potentially, right? Because schema is your friend. Schema is what stops you running a char value into an int field and learning about it 6 months later when your app crashes. So, again, trade-offs. I put this slide together with pros and cons because I wanted to illustrate a point I made earlier, which is that I, at least, do not believe those who say that NoSQL owns the future. Because there are scenarios where NoSQL is just the right answer. But there are scenarios where relational is a whole lot better. And arguably, especially in enterprise contexts, arguably the NoSQL category is bigger than, I'm sorry, the SQL, the relational category, is bigger than NoSQL going forward. We'll see. But clearly, there are trade-offs. Clearly, both are going to matter. Okay? So, let's talk about the first of our NoSQL technologies, DocumentDB. As the name suggests, it's a document store. No big surprise here. When I first heard about document stores, when I hear the word document, what I think of, what I thought of originally, was Word documents, Excel documents. Nah, they don't mean that at all. They mean JSON documents. And so, in DocumentDB, you can have a database that contains some number of collections. Each collection contains some number of JSON documents. So, for example, I've got here a DocumentDB database that's storing data about the users of my online game. Remember the example before for relational? I showed their age and so on. Okay. I'm going to do the same example, but now a document database. There's the first document. If you've not seen this before, that's JSON. Just texted, quotes, and so on. Very simple format. This says my first user's name is John. He's from Canada. He's 43. He last used my game March 4th of last year. Great. Simple. A second document in this database is about another user, Eva, who's in Germany. Actually, they'd say Ava, wouldn't they? But Ava, who's in Germany, who's 25. And now here you might notice, for some reason, I don't have her last use date. Well, that's okay. Just leave it out. There's no schema. No problem. Leave it out. Here's a document for a third user. This is Lou. He's in Australia, 51. I don't have his last use data, but hey, I've got his first use. Let's put that in instead. That's fine. There's no schema. Or how about this? I can have a fourth document that doesn't describe a user at all. The fourth document just says, you know what? In this database, there are a total of 3 user documents, last updated May 1st, 2014. There's no schema. That's fine. So, I'm guessing that some of you, for whom this is brand new, are saying, no schema, this is glorious. And some of you are saying to yourself, no schema, this is chaos. And I think both those things are probably true. It puts more burden on a developer to think about to get this right. But that's a simple example of a document database, a collection in a document database like DocumentDB. Applications can access this data, and they get back, unsurprisingly, JSON. Get back JSON. In DocumentDB, often referred to as just DocDB, in DocDB, there are a few different ways to work with data. One of them is, for basic CRUD operations, create, read, update, delete, there are RESTful services. You can just invoke these RESTful services to access data, read, update, and so on. Brief digression again. Isn't it amazing how fast RESTful interfaces crushed SOAP? Remember SOAP, anybody? Right? It was the big deal, right? At Microsoft, IBM, everybody, SOAP was the answer. And then REST came along, and SOAP just got smashed like a bug. It was remarkable. There's also a query language called DocumentDB SQL. It has a SQL-derived syntax. Simple example here. Selecting age, Lou's age, I think I showed you before. But don't be too excited. It's actually an extended subset of SQL. So it looks like SQL, but it's not full SQL because this is not a relational system. But if you want a query language, why invent a new syntax when everybody knows SQL? They chose instead to build on SQL syntax and thus on your knowledge to create a query language for a non-relational system. You can also write stored procedures and triggers and things called UDFs, all of which are built in JavaScript. So this is important. So DocDB stores data in JavaScript object notation, JSON. It also has, as the language for building stored procedures and triggers, JavaScript, excuse me. So in some sense, it's a native JavaScript environment. But do not be confused. As a client application using this guy, your client can be in JavaScript or C# or Java, other languages. They provide libraries for languages, and it's just REST. So if you want to, you can just create the REST calls natively, anything you want. Don't be confused. Even though DocDB is itself pretty JavaScript-oriented, the clients that use it, apps that use it, can be in all kinds of languages. Essentially anything through the raw RESTful interface. One more interesting point. Here, if you're going to get transactions, you must do it in triggers and stored procedures. You can't do transactions through CRUD interface, only in that logic that runs in the database itself. All right, so here's a possible scenario. It is plausible, I think, that going forward, this might become the way in which we commonly build, by default, new web-scale applications. On Azure, there's this thing called websites that's being merged into this larger category of app services going forward. You might have clients, mobile web browsers, that are written in JavaScript or something else, but they send JSON across the wire. Websites is actually based on Node.js. And Node lets you write JavaScript server-side code. So, okay, that's cool. JavaScript over here, JSON in between, JavaScript over here on the server. If the store I'm using is DocDB, I've got JSON, 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 JavaScript, JavaScript. That's kind of nice, isn't it? Scalable, cloud-based environment, consistent languages across the whole world, just about. Data formats are JSON everywhere. One could well imagine that that's the new default for building web-scale apps going forward. We'll see. We'll see. All right. Sharding and transactions. In DocDB, as I said before, you group the documents into collections. Collections are the shards. The unit of sharding is a collection. If anybody knows Mongo, this is a big difference from Mongo. In Mongo, collections and shards are disjoint. They're separate concepts. Not here. Here, a collection is a shard. And so, unsurprisingly, atomic transactions in DocDB can only take place with documents in the same collection, in the same shard. As I've said over and over, that's a typical limitation of sharding, that you lock your transaction to just data in that shard. So that's how it works here. Time for another technology basics discussion. And if you've not seen this topic before, replication consistency, this is kind of a take a deep breath topic. If it's brand new to you, it's a little complicated. So let's talk about this. So I've got a shard, right? I've got some shard in my database. It makes really good sense in many situations to replicate that shard, have multiple copies. And often it's done with one primary that's read-write and some number of read-only secondaries. That isn't required. Some of these guys actually do a multi-master replication. But my simple example here happens to show primary and secondary, which is fine. Why do you do that? You do that for a couple of reasons. For performance, because now reads can access multiple copies. They're not all sent to the same instance. It can go faster. And availability. I can lose a machine and a shard still keep on functioning. So replication of shards makes very good sense. Don't confuse replication with sharding. Sharding means breaking your database up into distinct pieces. Sharding means taking one of those pieces and copying it, replicating it. You do both of them in most NoSQL systems, okay? At least those I'm familiar with. But it's a good thing. It makes things faster. It makes them more available in the event of errors. But it brings with it, like almost every good thing, some pain. And the pain is this. The pain is this. When an application writes to the primary replica, that update, that change, will eventually propagate to secondaries. But it'll take some time. Given that, what does a reader see? What does a reader see? Because if you write here and make a change, and the reader happens to go to a replica, a secondary, that has not yet been updated, they're going to see old data, right? Was that okay? I don't know. What do you do here? Turns out that there are a couple of approaches that are very common right now. And there's a couple more that are not so common, but are in DocDB. Let me describe these approaches. And the example I'm going to use is DocDB. Turns out that to answer that question, what does a reader see, depends on what you're doing for consistency. One approach, one very common approach, is called strong consistency. Here's what that means. It means that when the writer writes to the primary and a reader comes into a secondary later on, the reader is blocked until that write propagates. Actually, the write won't return. That's a better way to say it. The write won't return until data is propagated across the whole thing. When the reader comes in, they're going to see the write data all the time. Strong consistency, because the write doesn't return until it's copied everywhere. What's good about that? Well, you never see old data. Readers can't see old data, and readers can't see out-of-order updates. Those are good things. What's bad about that? It's slow. It's slow. All right. The other alternative that's commonly used out there is known as eventual consistency. Here, what you do is interesting. The writer comes into the primary, in this example, does the write and just returns right away. A reader comes in. If the reader is sent to the primary, they'll see the current data. Great, they got the right stuff. But if they're sent to a secondary that has not yet been updated, what are they going to see? Old data. So, with eventual consistency, you might get old data, you might see updates out of order, but it's really fast. With eventual consistency, what they're saying to you is, we might give you the wrong data, but you're going to get it really fast. And you might think, well, that's stupid, right? What stupid, right? Who wants it wrong? But in practice, there are many situations where it's worthwhile. For example, by illustration here of an online game, you've got a leaderboard for the game, people who are winning, the highest scores so far, 10, 20 people. When you do a write to update that, and I do a read a millisecond later, if I see data a few milliseconds old on the leaderboard, does it matter? It does not matter, probably. There are plenty of situations where delivering fast data matters more than it to be exactly correct. And so there actually are situations, not banking data updates, I hope, right? But there are situations where eventual can make sense. So what DocumentDB does is supports both of those things as options you can set. It supports more as well. It supports this thing called bounded staleness, where in essence you can tell it how long you can access old data. You might see old data within a defined interval, and it's pretty fast, or there's this thing called session consistency, where you will always see your own writes, always, but you might see old data, out of order data, for writes by other applications, other clients. And that's pretty darn fast, and that turns out to be the default. That's the default in DocDB. So this issue of how to do consistency, strong, eventual, or something else, runs throughout the NoSQL world. I've illustrated it here with DocDB. We're going to see the same issue arises in other technologies. Trade-offs. There are always trade-offs. Here's our table. DocDB is a document store. Collections and documents are the core abstractions. You can be really big here, hundreds of terabytes, because you're sharding. The query language, we discussed earlier, an extended subset of SQL. Transactional support, yes, within the shard. All documents in the same collection can have transactions. Secondary indexes, yes. DocDB, I didn't tell you this, DocDB creates a secondary index on everything. You put JSON in there, it indexes it, everything, automatically, which is interesting. You can search for things fast. Stored procedures and triggers, yes, in JavaScript. Pricing, it's just like, well, it's analogous to the same model as SQL database. Here's the throughput. So what they're trying to do, one could argue, is give you the best aspects of a managed relational system, along with the best aspects, such as scalability and NoSQL, of a NoSQL system. Okay. Great. Next, tables. This is the oldest NoSQL technology in Azure. It's been here since the beginning, a long time ago. Well, 2008, 2009, that's a long time in our world, right? And here's the idea. And I regret, I apologize up front for the fact that this diagram is going to look complex, because they're not. Tables are not complex. But my diagram looks kind of complex. I've worked with this for a long time. I can't make it any simpler. So don't be put off by the apparent pictorial complexity here. At Azure, you've got these tables, but they're not really tables. I really wish they weren't called tables, but they are. Each table contains some number of partitions. I've called them A and B here. What's a partition? It's a shard. It's a shard, okay? Each partition contains some number of entities, which are sometimes called rows. They use those words interchangeably here, entities and rows. Each of those entities contains some number of properties. So, one property is always the partition key, which indicates which partition this entity is part of. Up there, for example, partition A, its key for partition is A. These two are both B. Identifies the shard, the partition. Next, a row key, an entity key, same thing. Uniquely identifying this entity in that partition. So you can see up there, there's A and 1, A and 2, B1, B2. Pretty straightforward, yes? Then each property has a name, a type, and some data. What I'm doing here is the exact same thing as before. I'm showing you entities that contain information about a user for my online game. So there's name, country, age, last use, just like before, and their types. For the second entity, just like before, I have name, country, age. I didn't have last use, remember? I leave it off, no problem. There's no schema here. For the next one, name, country, age, and first use. Remember that? I didn't have last use, put in first use. And the last one I showed you in DocDB, same data here, was a count of how many, in that case, documents, in this case, entities, there are right now, and the date of last update. So that's a reflection of how that same data might look in a key value store like tables. Why are they called key value stores? Because to access that data, you do this. An application provides a key, which consists of the partition key and the row key. In this case, for example, the key is B2. That says partition B, row 2, right down here. What you get back is that data. In this case, the count and the last update, last change. Okay? Simple. Really simple. Key value stores can be tremendously simple. Why is that good? Because they're tremendously fast as well. They can be very fast. In tables, Azure tables, sharding and transactions are handled in probably obvious ways by this point, right? As I told you earlier, partitions are shards. So the unit of sharding is a partition. And of course, there are transactions, but they only work on entities, rows, within the same partition. Not surprising. This thing also supports replication, of course, of partitions, and reads and writes provide strong consistency. If you get a chance on the show floor today, you might find some of the guys from the engineering team of tables. If you get a chance and you find these guys, say to them, so, isn't strong consistency really slow? Why don't you do eventual as well? And they can talk to you about this very cool mechanism they have that they will assert makes strong consistency as fast as eventual, or nearly as fast. It's very interesting. Their approach is interesting here. So, one more example. Let's summarize this guy first. Key value stores, in this case, have tables, partitions, entities. They can be very big. There's really no query language. That's too strong. There's a little one. If you know what OData is, OData, who knows what OData is? Anybody? Oh, good. OData's got this simple query language built in, and tables support a subset of OData queries. Most often, though, from what I've seen, people access things by providing the key, get the value back. But there's other choices as well. Transactions are, of course, inside the shard, the partition, like I said before. There are no secondary indexes. There's no stored procedure support or trigger support. But you're only paying for, this is interesting, you're only paying for the storage, the gigabytes. And so tables can be really fast and incredibly cheap. If you want to have massive log data, for example, that you access very quickly like that, that's a classic scenario for tables. They're really cheap because table storage costs the same as blob storage in Azure. It's really cheap. All right, one more. HD Insight HBase. This guy's a column family store. The roots here of this technology are in something called Bigtable, which Google invented a while ago and then published a paper on. Various people then attempted to implement that technology. So HBase, for example, which we'll see in a few minutes is part of the Hadoop family of technologies, is an open source implementation of Bigtable to a great extent. In the Azure world, HBase is part of the HD Insight service, which is the Hadoop-based service we'll talk more about in just a few minutes. And here's the idea. In HBase, you have tables. But this time, they really are tables. They really are tables. They have columns, they have rows. So, for example, one column is called the row key. You can then have other columns like name, country, age, last use, first use. Again, it's my same example. But the columns, as the name suggests, are grouped into column families. It's a column family store. So the first family is user. The columns contain data about the user, their name, their country, their age. The second column family is about usage, last used, first use, and so on. Okay? What's interesting here is that at runtime, when you're using this guy, you cannot add column families dynamically. You can't. But you can add columns. At runtime, you can add new columns, which is really interesting. I'll tell you why in just a minute. Then there are rows, and the rows have row keys, unique identifiers, and data. Now notice some things about the data. It is possible to have multiple timestamp versions of the data in a single cell. It's possible. And so when you, as an application, do a query, you can specify the column family, in this case it's usage, the column, last use, the row, 2, and the version 2 up there. That's interesting. What you get back is that data, and there's support in HT Insight for an open source extension to this called Phoenix that lets you do SQL. Again, it's not full SQL. It's SQL-like, SQL-derived queries on HBase. So you need not just do those simple requests. There's more powerful query support as well. So what's interesting about this? A lot of things, actually. Notice, first of all, that there was a bunch of holes in that table. HBase is designed to support tables that are very sparse, with lots of holes. Suppose, for example, that you, in your application, want to have in this database a column that stores information for just one row. Maybe only one of the rows you're dealing with has this kind of data. You are allowed to add a new column to a column family and use that just for a single row. Because HBase is designed, as suggested by Bigtable, its original name, to support tables that are incredibly large, tables with millions of columns and billions of rows. We're talking Bigtable. The example Google uses in its original paper on Bigtable is a table designed to store URLs of the entire web. This was designed to be a giant table for the whole web. Each column was a kind of data on the page. And so you were allowed to add a column for whatever you wanted to do. You could make really huge columns. And if you want to store data about just this thing that only you care about in your app, you can do that. You can add your own column for just one row if you want to. Designed to support massively sparse, very big tables. And notice something else. Each row has a row key, and they're unique. But look, they're sorted. They're sorted. I want to be clear here. I'm using American English. I'm saying sorted. If I were British, I'd be saying sorted, right? Sorted. They're not sorted in the sense of sleazy, S-O-R-D-I-D. I mean sorted, in the right order. Just to be clear. So they're sorted. Now that's interesting. And it corresponds to something else interesting, which is to be this big, millions of columns, billions of rows, clearly it must be sharded, right? And it is. It's sharded. But previously, the shard boundaries have always been visible to the application developer. Collections in DocDB, partitions in tables. Here, you see no shard boundaries. What's that all about? Let me show you. This is very interesting. HBase has units of sharding called regions. But you, as a developer, will never see those regions. HBase automatically shards the table. How? By using that sorted row ID. Because they're sorted, it can move things around to make sure that the regions all contain contiguous sets of row IDs. It can even rebalance dynamically over time. You, the user, never see the shards. It automatically shards for you, which is cool, isn't it? But, of course, you have to know that whenever something is cool, it means there are trade-offs, and you're going to lose something. So what do you lose? Answer is this. Previously, when we saw sharding, we saw that the shard was the transaction boundary, right? And the user, you for example, were able to figure out that transactions must be scoped to just that shard boundary. If the user cannot see the shard boundary, the developer, then how could the developer scope a transaction to the shard boundary? You can't. You can't. And so in HBase, transactions can span only a single row, just one row, not the whole region, because the developer can't see the region. Okay. I hope you think this is interesting. I love this stuff. I think this is very cool. When you walk through the technologies, they've got these very strong similarities. They all do sharding, transactions, strong consistency or eventual or something else. This guy also does strong, okay. But they have different data models, so the approach is different for all of them. All right. Column family stores, like HBase, tables, rows, columns, lots of abstractions here. They can be very big. Without the SQL subset in Phoenix, there's not much queryability here. With Phoenix, you can have this SQL subset for queries. The transaction boundary is quite small, all cells in the same row. There are no secondary indexes. There is support for something called coprocessors in Java, which are analogous to stored procedures. And the way it's charged on Azure, you pay for storage, plus you pay for VMs per hour because you're running on a cluster, an HD Insight cluster, and you're paying for the VMs in the cluster. So there's a summary of the core NoSQL services in the upper left-hand corner of my 4-quadrant diagram that I showed you a while ago. I hope this is helpful, but we're not done yet. We've got a lot more to go. Moving to the upper right corner of that diagram, NoSQL, at least non-relational, big data analysis. That is the world of Hadoop. But here's what's happened. Hadoop began life as a clustering technology with support on top to build applications that processed big data in parallel. It was originally about big data analytics. What's happened since then is things have changed. So the Hadoop technology family runs on a cluster of machines, physical or virtual. The bottom technology is this thing called HDFS, the Hadoop Distributed File System. What this guy does is lets you have really big files. You can have files that span multiple machines. So a file need not be constrained by a single machine's disk. They can be really huge. Turns out, that's a lot like blobs on Azure. It's a lot like Azure blobs, a point I'll come back to in a couple of minutes. On top of that in Hadoop today is this thing called Yarn, yet another resource negotiator, that lets you support diverse technologies, because originally this guy supported MapReduce, a way to do parallel analysis jobs on big data. Now it supports MapReduce, something called TES, other options as well. What those guys let you do, I'll show you in a minute, is build parallel applications that process HDFS data, the classic unstructured big data analytical applications. That's where Hadoop comes from, MapReduce. Another Google technology originally, published in a white paper, an article people then built open source versions of. But now, other things have happened. So for example, you can build raw MapReduce applications if you're really tough, but most folks use simpler things on top, like Hive and Pig, more open source technologies, to build those jobs more easily. And you can tell, can't you, this is all open source stuff, because no product manager in any company would ever call his or her product Pig, would they? Never happen. But now in HDFS, there are things like HBase, which I just showed you. HBase is for operational data, but it's part of the Hadoop technology family. It's not just analytical data. And there's even things like Storm, which are for stream processing, like Azure Stream Analytics. So the Hadoop family has moved away from being just about MapReduce and just about analyzing big data in parallel to include a lot more things like HBase and Storm for operational and streaming data. Arguably, Hadoop is a clustering technology on top of which people are building a range of things. Azure has this thing called HD Insight that provides all of these and more, they keep adding to it, as a managed service on top of Azure. So you need not create the cluster, manage it, and so on. You can just say, Azure, give me a Hadoop cluster, and I want to run HBase. I want to run a TES application, whatever, on top. Here's how those applications work. For doing big data analytics, I want to run things in parallel. I want parallel access. And so what I can do is use either MapReduce, the older version, or TES, an updated version, or other things as well, to build an app that's parallelized, run in multiple VMs across my Hadoop cluster. It can then access data that's actually stored in Azure Blobs. Remember I told you that what HDFS does, creating this API on top of a big file system, is much like Blobs. So what Azure does in HD Insight is actually implement the HDFS API on top of Blobs. So it looks to an application like it's talking to HDFS, but underneath it's actually Blobs. That's important because it means you can run standard Hadoop apps on this technology, HD Insight, on this service. And to re-implement Blobs would make no sense. So the API sits on top of Blobs. If you saw the announcement last week of the data lake technology on Azure, that is somewhat similar. The data lake technology puts HDFS API on top of Blobs. It's not exactly the same, but it's somewhat similar. So then I can use Hive and Pig and so on, and even in Microsoft's implementation, you can use Excel to submit requests to Hive in this language called HiveQL, which in turn can generate MapReduce. So from Excel, I can submit big parallel big data jobs on HD Insight. It's interesting. And don't be misled here. I show 3 VMs. In fact, clusters are commonly 10, 15, 30, 50, much more than that. It won't fit in my slide. All right. I want to end with another place. Because in the world of NoSQL, people think of document stores and column family stores and so on. I want to end with a technology that is actually not NoSQL in the conventional sense, but is non-SQL. It's part of what I want to think of as the SQL Plus world. It's relatively new for Azure, and it is, I would argue, really important. It's Azure Search. Let's look at this. Suppose you got an application, and your app has data in a relational store, NoSQL store, some operational data, of course, and you do reads and writes on that data. Great. That's what apps do. Suppose, though, that you also want to put a search box in your user interface. Why would you do that? Easy. Because users love search. Don't you love search? I love search. Give me a UI with a search box, I'll use it all the time. People love search. And yet, to build a search engine that searches across your operational data, well, that's no simple task. To deploy an open source one like Elasticsearch, again, no simple task. What Azure Search does is the following. It gives you a search engine that your app can use. Azure Search is not about giving search support to end users. There's no UI component, at least not yet. Azure Search exposes RESTful interfaces that apps can use. The point of Azure Search is to help you build applications that can have a search box in the UI. So, why would you do this? Well, online retailers. If you're a shoe store, for example, and you've got no search box, you're dead in the water. No one's going to use you, right? If you are a user-generated content site, like a discussion site for movie buffs, people want to search for their favorite movie to talk about. Search is so important, even enterprise apps. Tell me, why don't custom business apps all have search boxes? We love search. It'd be so easy to use. The answer to that question is it's been too hard to build. And Azure Search is designed to make it so that anybody can build apps that have a search box in the UI. So, here's an example. Suppose I'm an online retailer selling shoes. In my UI, I want to put a search box. Now, it can be anything. Azure does not provide UI components. What I'm showing here is what seems to be the international standard for a search box. But anything you'd like. You can even do maps for the search interface if you choose to. But here's a simple example I made up that lets a user type in like hi, and then what do you expect from a search box? You expect suggestions, right? High heels, high tops, high arch. And so Azure Search lets your app make requests, RESTful requests to the search engine at every character typed. It'll return suggestions, which you had to define yourself earlier in the engine. Then the user picks one, and what happens? Well, you get results back. Users expect the search term to be highlighted. And so Azure Search returns those results highlighted for HTML. High heels, and so on. But here's the important thing. The important thing is Azure Search lets you control the order in which those results are returned. And that's a big reason why you would use it. Because you can use Bing or Google to do custom search in your data, potentially. But you can't control the order of the results. Here, as I'll show you in a couple of minutes, you have control with interesting mechanisms over order the results are returned. Why is that important? Well, if you're a shoe store, maybe one of your shoe sellers is going to pay you money for a month to promote their shoes at the start of the search results. And you're thinking, well, that's kind of sleazy, isn't it? Right? I want honest search. I don't want paid search. Yeah, well, welcome to the world. Right? That's where money comes from. And so being able to control the order of search results is really important in many situations. And that's a big reason why people would use Azure Search. Also, notice this. Notice that here I'm showing pure text-based search. Search results, sorry. If you did this as a shoe store, you'd be dead in a week. You've got to have a better interface than that. So Azure Search lets you create much better interfaces than that. It provides more information to the simple text UI. It also lets you do things like over on the right there, color and price, that helps the user's next search. And I'll show you what happens there, what supports that in just a minute. So the point of Azure Search is to help people like you build apps that have search interfaces like a search box and do that more easily and to control the order of the results. Okay? I got to tell you, I hate having speaking slots right after lunch because all the blood's in your stomach, not in your head, right? Yeah, you're nodding fervently there, right? Yes, okay. We're almost done. So what do? To use Azure Search, you start by creating an index for your app. You define the schema for your index. Then you must populate the schema. So here's an example schema for online shoe retailer. These are the columns in your index. Might be one for category. What category of shoe is this? High heels, sneakers, what? It's a string, and it has a bunch of attributes. Look at this. It can be searchable. It'll get suggestions, return suggestions back. You can sort based on this. You can retrieve it, and you can filter based on this as well. You might also have in your index the brand, same attributes, the style, same attributes, and you might have color. Well, color is a collection of strings because the same shoe might come in many colors, black, white, red, and so on. And so the attributes omit sortable. You can't sort based on a collection, only in one value. Or how about this? Price. It's a double. Price, you can't have suggestions. That'd make no sense for price. But it's got this thing called being facetable. That's not face table. It's facetable. And what that means is that you could ask questions about this, like how many are there at this price? If it's facetable, you can ask questions like that. Give me the number of entries between $10 and $50, for example. That's what facetable means. Then I can have a picture, which is only retrievable, because all that string is URL pointing to probably a blob with a picture of the shoe in it. And then look at this in my example. The last two items, stock, which is the count of how many are in stock of this shoe, and promotion, a Boolean. Is there a promotion on this shoe? Those guys are not retrievable or sortable or filterable or anything. Why would you have things in your index you can't access? The answer is you can use those to control the order in which results are returned. And I'll show you how in just a minute. Okay? And some of you are thinking, this is a lot of conceptual technology in a short time. Sorry, I don't want to waste your time here, right? But if you're interested, I've actually written white papers on almost all of these technologies that go over this in some more detail. I'll read about them later on. They're on my website. They're on Microsoft sites as well. So, once the index exists, you have to add data to it. And it might look like this. There's an entry for sneakers, Contoso brand, high tops. They come in white and black. There's the price, the link to their picture. You've got 194 in stock, and there's a promotion. There's a promotion on these guys. High heels, again, Contoso, pumps, they're red, blah, blah. Look at this. Number in stock is huge, 285. The buyer loved those. Whoa. You got a promotion. And then look down at the rest here. You can see, if you look at this, there are promotions on all the Contoso offerings, and there's a whole lot of those Contoso red pumps available, way too many. So that's what's actually in your index. When you do a search, it looks like this. The user enters, let's say, high heels in the app search box. The request goes to the Azure search engine, which returns back the result and displays the UI to the user. With my example index I just showed you, a search for high heels would return the stuff in pink there, in purple. You would not see any of these guys because those, remember, were marked as not retrievable. But you can use those to define the order in which search results are displayed. So look at this. Here's that UI again. Notice that Contoso shoes are above Fabricam. Why? Because Contoso is paying us to do a promotion. Notice also the Contoso pumps appear upper left, the prime position. Why? Because there were so many in stock. The buyer bought a jillion of them, want to get rid of them. So based on values in the index, you can have the search results appear in specific ways. You can define these based on business reasons. And over on the left there, those guys were all facetable, remember? Facets make that possible. So, I've got 3 minutes left. I'm going to go over by about 1 or 2 minutes. Forgive me here. I want to wrap up. Before I do this, please start building apps with search boxes because I want to use them. Everyone loves search boxes. The point of this is to make it easier for anybody to build apps that have search in the UI. Okay? And finally, let's pull back again and do a few slides on an even bigger picture. Traditionally, applications are used by end users, which have operational data, relational databases, and they have relational data warehouses. We build applications in-house for internal users to work with that data. Look familiar? You all have this in your organization today, probably, right? Going forward, what we're going to see is, yes, this, but it gets bigger. Applications now use relational and NoSQL databases. The implication there is that we have to have analytical data that's both relational and unstructured, non-relational. We're going to build apps that access both of those things, and we're going to have search data because search is its own category, disjoint from those two. To support a search box in the UI, you've got to have something to do that. And so when you think about Azure data technologies in the SQL Plus world, with that diagram, they look like this. If I want an Azure-based service, relational data warehouse, I can use SQL and IaaS VM. I can also announce 3 days ago, 3 working days, I can use SQL Data Warehouse, just announced, which lets you have relational data warehouse in the cloud. That's interesting. You can also have that same technology do unstructured data in the cloud, and there's also Hadoop for that on Azure. Here, this is SQL Database as a service, or a SQL Server and IaaS VM. Here, we saw a bunch of things, DocDB, tables, HT Inside HBase. And this, of course, is Azure Search. So, Azure has this broad set of technologies as managed services to use for this brave new world of data. And once again, if I'd had more time, it was just announced last week. Right here, and actually across both of these, should be SQL Data Warehouse, just announced last week, to fit in both those spaces. So, my last summary here. A SQL database makes sense when you want relational data, you want to manage service, and thus you get your apps up as fast as possible and do minimal management. You want to use DocDB, tables, HBase when you want NoSQL. More scale, non-relational data model, and no schema, more flexibility. You want to use Hadoop, Tez, MapReduce, the technologies for big data analysis. And if you want to do search, that's an Azure search story. Straightforward. So, I began here by asserting that NoSQL technologies are fundamental to Azure today. Do you believe me? I hope so. It's very true. It's very true. We talked about several of these, walking through what they're like at a conceptual level. My last thought here is, welcome to the SQL Plus era. You are going to like it. Thank you very much. If you have questions, please come talk to me, okay? Thanks.